Okay, welcome to lesson 36. So this video is going to walk you through how we actually derive the finite difference method or representation for a second derivative. Though I could give you the equation, what's the fun in that? And also, you have all of the tools you need to actually derive this, and you've actually had them since Calc 1 or Calc 2. So what we're going to do is we're actually going to use Taylor series. And I know this might scare some of you, but you'll be all right. So what we're looking for really is, let's say that we have a function f of x plus delta x. Now, this is what we talked about in topic 1. You've seen this notation before. What I'm actually going to do is I'm going to use x plus h, just because h is faster to write. So h is equal to delta x. I'm just using this notation because I don't feel like writing delta x over and over. So what we're really interested in doing is we're trying to figure out the second derivative. And so sometimes one method we use to, well, I don't know what else to do, is let's just look at the Taylor series representation of f of x plus h. So that's what somebody did. So f of x plus h, using the Taylor series expansion, and you'll sometimes see me write TSE, is as follows. F of x plus f prime of x over 1 factorial. I just write this so you see the pattern, times h, plus f double prime of x over 2 factorial h squared, plus f triple prime of x over 3 factorial h cubed, and then just for fun, f of the fourth derivative, I'm not going to write quadruple prime, x over 4 factorial h cubed, or h to the fourth, sorry, plus dot, dot, dot. Okay. So we're interested, of course, in the second derivative. And it would be really nice if I could just solve the equation for this f double prime of x term. There are a couple of issues with this, though. So again, our goal here, solve for f double prime of x. Remember, we're trying to get the some sort of representation, some sort of finite difference of the second derivative. So a couple of things we can note here. So let's observe that each successive term in this Taylor series actually gets smaller, right? So this Taylor series hopefully converges. So notice that you have 3 factorial in the denominator, then 4 factorial in the denominator. So this each successive term, gets smaller. And this is good. Otherwise, we can't let this Taylor series represent an actual function if it diverges, right? So maybe the thought here is that we could potentially neglect, f triple prime of x term, f, quadruple prime of x, dot, dot, dot. But if we did that, if we neglected these higher order terms, which is what they're called, we would still be stuck with this very pesky and annoying f prime of x. So this guy. This is a bit of an issue. So we need to get this term to go away somehow. So we need it to disappear. So observe the clever trick here. What we're going to do next is just find f of x minus h, because why not? So if you do this, what will happen is you start to see some alternating signs. And what I'm actually going to do is I'm actually going to rewrite the f of x plus h underneath, hopefully without some of my notation here, just because you can actually see what happens. So let me clean this up a little bit. Okay, so it's nice to see the equations right next to each other. So let me get rid of all of this extra stuff that is going to get in the way. 1 factorial, this is 3 factorial. Okay, So f of x minus h is going to be f of x minus f prime of x over 1 factorial times h plus f double prime of x over 2 factorial h squared minus f triple prime of x over 3 factorial, and then plus the fourth derivative of f of x over 4 factorial h to the fourth. Oops, I forgot h cubed here. Plus dot dot dot. Okay. So you can hopefully some of you notice that because of the alternating signs in the f of x minus h equation, what actually ends up happening is if we add f of x plus h and f of x minus h, these odd derivative terms, the odd ordered derivatives, actually drop out. They disappear. So let me write this out. F of x plus h plus f of x minus h equals, so if I do this, I have 2f of x, which is not a problem, plus 0, and let me just put a note here that this is the f prime of x terms. That's sum to 0, plus 2f double prime of x over 2 factorial h squared minus, 0, right? Or plus, doesn't matter. So these are the f triple prime of x terms. And then plus 2f, fourth derivative of f x over 4 factorial h to the fourth plus dot dot dot. Okay. So hopefully you're starting to see this interesting pattern that, as hoped, the f prime term actually dropped out. In fact, every other term ended up dropping out. So good for us. So really all we needed to do is get this f prime of x term to disappear so we can attempt to isolate f prime of x. So that's what we're going to do now. So I'm just going to move a few terms over. So I'm just going to start rearranging here. So on the left-hand side, I have f of x plus h minus 2f of x. And that guy came from right here, okay? Plus f of x minus h. And this is equal to, so 2 divided by 2 factorial, by the way. I didn't make that correction up here. That's 1. So on the right-hand side of the equation, I have f double prime of x times h squared plus some term basically with this fourth derivative. So I'm not going to do any weird simplification. F the fourth of x over 4 factorial h to the fourth. I'm not doing any simplification because I don't really need to, because that term is eventually going to disappear, or at least to become neglected. So notice this h squared term. So what I'm going to do is I'm actually going to divide every term by h squared. So on the left-hand side, we have f of x plus h minus 2f of x plus f of x minus h divided by h squared. And that's equal to f double prime of x. Now, here's the interesting trick here. We have these other terms. I'll just rewrite them again. For f to the fourth power h to the fourth. Okay. So plus dot dot dot. We still have these other terms. So what are we going to do with these other terms? So the idea here is exactly what we noted back at the very beginning, is that each successive term in the Taylor series gets smaller and smaller. And actually, we've made it even better for us, even more convergent, because we ended up eliminating every other term. So the terms are going to get smaller faster because we have fewer terms. Okay. So, or we still have an infinite number of terms, but each term is going to get smaller faster. So what this ends up becoming is f double prime of x is approximately equal to this quotient over here on the left. I'm just going to reverse the order here. F of x plus h minus 2f of x plus f of x minus h divided by h squared. Now, and actually, sorry, so I divided by h squared over here and I didn't fix it over here. So if I divide every term by h squared, I get h squared on this fourth derivative term. And so each term is going to have a, h to the power 2 less than what it was before, since I divided every term through by h squared. So sorry about that. Good on you if you noticed. All right, so plus, now I'm eventually going to just neglect the rest of these terms. So what I can do is sort of group them together and say that they're all order h squared, right? So these are basically the higher order terms, plus, all these other, well, actually what I can do is I can say plus higher order terms. And what I do is I just take the h squared, right, from the first term I'm neglecting, and that ends up becoming my accuracy. So what I can say is that f double prime of x is approximately equal to this quotient. Okay. Copy. And this quotient has order h squared accuracy. And the funny O, and let me try and write this better, this funny O, you actually saw this in a previous lesson. So it just means order of, and so hopefully you remember that notation. And this final equation that we've arrived at is called the central difference second derivative. So again, I haven't introduced any crazy math. I think you need to have a bit of an inspiration to think, oh, maybe I should just add f of x plus h and f of x minus h in the Taylor series approximations. But mercifully, someone else already figured this out. So all you need to do is know where this equation came from. And then you end up with the central difference. So we will be using this equation in the next 3 lessons for sure.